So let's get started on lecture 17 on the course Proof Complexity as a Computational Lens, the first lecture after the winter break. So we're going to continue talking about space complexity, mainly in resolution and polynomial calculus. Today whenever I say polynomial calculus, I mean PCR, that is, we have dual variables. That's going to change tomorrow, but not today. So first, we want to compare, the main focus is to compare closed space in resolution and monomial space in polynomial calculus resolution. And this is also recapping some of what we've talked about. So what do we know? Well, we have the same lower bounds, tight lower bounds, for many of our usual suspects. So what do we know? We have pigeonhole principal formulas. Even if you make them into graph pigeonhole principal formulas, that is, every pigeon can only fly to a limited number of holes. We have Thapen space lower bounds, except that Thapen lower bounds for expanders. The slightly weird thing, though, is that we need double copies of each if we want it for polynomial calculus. What we saw last time was random k-CNF formulas. And we only proved the PCR space lower bounds for random 4 CNF formulas. You can get them for 3 CNF formulas. It's the same ideas, but just more pain. And this is due to a sequence of works mainly pushed by Bonacina and Galesi. But some things remain open for PCR. Although I think it's reasonable to say that we expect to have the same lower bounds. So for instance, slightly weirdly, if I take the pigeonhole principal formula, which has wide clauses, and I just use auxiliary variables to turn it into a 3CNF, then the space lower bound for polynomial calculus resolution breaks. Also, if I add functionality axioms, which usually doesn't change things too much, except that it can make our life more complicated, we've learned for algebraic proof systems, again, the lower bound breaks. For Thapen, we already said if we don't want these double copies of edges, we don't have tight lower bounds. There are a number of different ordering principles that we've talked about. We talked about this, that we have a partially ordered set, a totally ordered set, so a linear order. There's also, we didn't talk so much, but I think we mentioned also that there are formulas in coding that I have a dense order, that is in between any two elements. If x is less than y, then there's a z that lies in between. For all of those, we have lower bounds, tight lower bounds for resolution, not for PCR. And my personal favorite, which you might have guessed, is pebbling formulas, where, to the best of my understanding, again, we have a very tight connection in resolution between pebbling time and space on the one hand, and resolution proof length and closed space on the other hand. It's very believable that the same thing should hold for polynomial calculus, but we just don't know. So in general, as will be the case for the last few lectures, whenever I talk about CNF formulas, I'm thinking about k-CNF formulas for some constant k. This is just to make the statement easier. So, and in particular, n will be the number of variables, unless stated otherwise. So let's maybe say this: f is a k-CNF formula over n variables is sort of a default assumption, unless I say otherwise. Then what we've also seen is that the closed space of refuting f is essentially lower bounded by the width of refuting F, except for some small constant, which depends on actually the K here. And this is by Atserias and Dalmau. We also know, so this already tells you, that closed space is lower bounded by width. And for most formulas that people have been studying in literature, we know that these two measures coincide, but this is not true in general. So we know that there exist k-CNF formulas, Fn over n variables, size n, such that the closed space in resolution of refuting F is almost maximal, n over log n, but the length of refuting F in resolution and the width in resolution of refuting F is minimal. So linear length and very small constant width. We do have actually a slightly stronger separation for polynomial calculus, which we talked about. It follows from, we didn't do this proof, but it kind of follows from some of the things we've been talking about. This is, if you take Thapen formulas with over an expander with double copies of the edges, then in fact you get formulas that have linear monomial space. The degree is constant, and the size of refuting these formulas is n log n. And the upper bounds are, the size upper bound is even in polynomial calculus. For degree, we don't care. The lower bound is even if you have access to dual variables. But the caveat is that this depends on the characteristic of the field. So I only know this has been proven for GF2, and then you use Thapen formulas. I believe you could probably do it for other characteristics. I don't know if anyone had the energy to work out the details. So we don't have it, in some sense, this is a slightly stronger statement for polynomial calculus than for resolution, but it depends on the characteristic. And so I guess what this is saying is that what I'm trying to suggest is that there are a lot of parallels here. And closed space and monomial space are behaving in similar ways, except for questions where we maybe believe that monomial space is similar, but we cannot prove. And so a natural question is, actually it's a reasonable question to ask for CNF formulas whether these measures are the same or not. And the slightly annoying answer to this question, or non-answer to this question, is we have no separations between closed space and monomial space. Now, if you go into details, the question is, how do you exactly define the monomial space? So for many of the lower bounds, or for all of the lower bounds, in fact, actually the monomial space measure, we're just counting the total number of distinct monomials. We're not charging for double copies. And you could say, well, let that be my measure then, so that meaning that in monomial space S, I could actually have 2 to the S distinct polynomials, but I don't charge you for this. In this more general definition of monomial space, there is a constant factor separation. Then we know that you can save, there are formulas for which you can save a factor 1/3, but only by having double copies of the same monomials. This is from the very first paper, Aleknovich, Bensason, Rasborov, and Wilderson, that introduced space, the space measure in general in proof complexity. Remember earlier, Esteban and Toran gave the definition for resolution, and then Aleknovich et al. Extended it. So this seems to be a pretty basic question whether closed space and monomial space are the same, or whether we should believe that algebraic proof systems are stronger, we just don't know with respect to space. So the main focus today, the main question that we would like to understand is whether we can get an analog of this. The analog of this would say that for any set of polynomials, the monomial space of refuting it is lower bounded by the degree of refuting. Okay, we're nowhere close to having anything like this, but we also cannot refute it. If you restrict yourself to considering CNF input, then you could make an even bolder statement or conjecture. You could say, is it in fact true that monomial space is lower bounded by resolution width? And I think maybe Albert Atserias is the first one to be on record articulating this conjecture. This we don't know. We do know two things. So basically, again, what do we want to understand? We want to understand the relation between monomial space and width. And the question we're asking ourselves is, could it be true that the resolution width of refuting a CNF formula is a lower bound on the PCR space? So we know that in fact, if you allow yourself to cheat, if I take a formula that has a high width lower bound and I XORify it, then the monomial space, remember XORification is for every variable, I just replace it by an XOR of two new fresh variables and then I expand out to get a CNF. Then it turns out that it can be proven that the monomial space is lower bounded by the width. And this is by Philus, Lauria, Miksha, myself, and Mark Venios. And the journal paper was finally out last year. The conference version is from way earlier, from 2013. But this is like the wrong bound, right? We don't want the XORification there. So what we want, the main thing we want to talk about today is a result by Galesi, Kołodziejczyk, and Thapen, which also was published as a journal version last year, but this is from 2019. And basically, they say the following. So basically, let me state their theorem in two ways. So Galesi, Kołodziejczyk, and Thapen basically prove this without any XORs, but they lose the square root. Okay. So what they're able to prove exactly is that if the monomial space in PCR of refuting a k-CNF formula is S, then the width of refuting the formula cannot be too large. It's at most S squared minus S plus K. And that is mainly what we will study today. It's a very interesting proof technique that is quite unlike, I think, what we've seen before, at least in this part of proof complexity. So I think it's interesting to study and try to understand it. In particular, because somehow the proof doesn't feel very tight. It feels like we're really losing a square root here. And I think you'll kind of see where we're losing the square root. And the question is whether anything can be done about that. As a byproduct of this, and as a warm-up, we'll look at another very nice result by Bonacina, which is another amazing result. Remember the total space measure. We haven't talked too much about it, but if you really want to measure space faithfully, at least up to logarithmic factors, then you should say, actually, let me count the total size of what I need to represent, which is scaling linearly, at least with the number of literals. Okay, so I'm assuming now that every variable has a unique name in unit cost. That's a little bit unrealistic. Probably like I need a logarithmic number of bits as the number of variables scale, but let's not argue about logarithms, okay? Then it's kind of clear that, well, let's just measure total space as the number of literals counted with repetition. Okay, then it's clear what can I say for almost any proof system? Well, most proof systems can simulate resolution. Resolution only needs linear clause space. How wide can the clauses be? Linear. Okay, so total space should be upper bounded by n squared in all the proof systems we're going to talk about. Pretty much, right? And what Ilario, so again, Bonacina and Galesi and Thapen, I think, proved that this is tight. There are quadratic lower bounds. And then Ilario proved something even more amazing. And we're going to see, so this is, I'll label this as theorem A. We're going to start by proving another theorem, which I'll call theorem B, which says that suppose that the width of refuting the k-CNF formula F is strictly larger than W, which is at least K, just to deal with corner cases. Then, in fact, the total space, and now let me be careful to write out that I mean resolution, the total space of refuting F is then at least W squared over A. So, in fact, if I have a width lower bound, then the total space is quadratic in the width. Are the statements clear so far? So, what do we need? So let's just recap also, because it's the first lecture after holidays. So we're looking at, when we're defining space, we're going to talk about sequential proof systems. That is, a proof is a sequence of lines. We also focus on implicational proof systems. That is, every new line actually follows, either it is a line in the input, or it follows implicationally from previous lines. There are also some special type of axioms. When we're in algebraic proof systems, we might have axioms saying that x and x bar take opposite values. X squared minus x is 0. Let's deal with them also as axioms somehow. They have a little bit of a special status. Okay, so we have a sequential implicational proof system. Then we can write it down as a sequence of memory configurations where we want, if this is supposed to be a refutation of a formula F, then we're starting with no constraint in memory. We're ending with contradiction in memory. And then for all time steps, t between 1 and tau, we get memory configuration T from the previous memory configuration by either an axiom download. That means that we just take an axiom from the input, or some Boolean axiom or complementarity axiom, and add it to the configuration. Or we do an inference step in the proof system, but the inference rules are only allowed to operate on what we have in memory. We'll be very relaxed. In fact, in everything we do today, the only thing we're going to use about inference essentially is that we know that it's semantically sound. So And this is also a general feature. If you remember, we talked about this before. All of our space lower bounds, almost all of our space lower bounds, will hold in the setting where I just use that things follow semantically. Except the total space lower bounds, you realize, cannot be proven in this setting, because in this setting it would not be true. So for total space, we'll need to be a little bit more careful. But for the PCR lower bounds, they will hold in the semantic setting. And then the third thing we can do is erasure. And erasure is just saying that, well, whatever. Okay. The memory configuration at time t is a subset of the memory configuration at time t minus 1. An axiom download is just saying that mt is mt minus 1 union some axiom, either from the input or a Boolean axiom or something like this. Okay. Now, once we have a measure like this, we can define the clause space. Recall, this is just the number of clauses. The monomial space of a configuration, if we're in one of our algebraic proof systems, is just the number of monomials. The total space is just the total number of leapfrogs. And then for any such measure m, I just say that the measure of a refutation is just taking the max over all memory configurations of the measure at time t. And I can also define the space measure of refuting, say, a formula f, and that would be the min over all refutations of f of this measure, right? Okay. So now I think we're ready to do. We'll start with doing the total space lower bound. And the total space lower bound again is also a special case of. It's going to be a very special case of the techniques that we use to get the result for monomial space. So we'll do the total space lower bound, and then we'll take a step back and try to generalize what we did and get a monomial space lower bound. So now, so we're going to relate space measures to width. So we need to understand width, and in particular, we're going to use that we have an exact combinatorial characterization of width, which is what we get from the prosecutor-defendant game, the game that actually Pavel Pudlak defined, and then that was rediscovered or independently reintroduced by Atserias and Dalmau, and they used it to say that actually, if you have this prosecutor asking the defendant about truth values of variables and trying to falsify an initial clause, axiom clause in the formula, and we limit the prosecutor memory, then this gives us an exact combinatorial characterization of the width, in the sense that basically, except for additive constants, the idea is that if the defendant can successfully answer questions in perpetuity, as long as the prosecutor has memory at most W, then essentially that means that there's a width lower bound W, except there's just +1 ratio. Okay? So let me write this down very carefully, because we're going to use this over and over again. So again, F is a k-CNF formula. Let me say that a defendant strategy. So let me now describe a combinatorial object that would be the strategy that the defendant could use to play forever. So a defendant's strategy in memory W is a non-empty family of partial truth value assignments which I'll write calligraphic 8, and it's non-empty, such that for every alpha in curly A, the following thing holds. So firstly, the domain of alpha, the size of the domain of any alpha is at most W, because we only need to play up to memory W. In fact, to save typing from now on, I'll just write the size of A to denote the size of the domain of A, just because that saves me like at least 5 characters. Any sub-assignment is also in the strategy. Because this is, whenever we have reached this position and then the prosecutor forgets some assignments, then the defendant should be able to continue playing by just forgetting exactly the same assignments. An even more important strategy is that if alpha is strictly smaller than W, and if X is a variable that is not in the domain of alpha, then there exists a beta that is a superset of alpha that is in the strategy and has X in the domain. Okay? Which means that when the prosecutor has memory and it asks about a new variable, prosecutor can continue answering by just extending the truth value assignment to beta. Note, we're going to use repeatedly that actually, without loss of generality, this beta just extends alpha with a value to X. Because if it does more, then I just shrink it down afterwards. Okay, but we will often use that we'll be interested in one variable, then we'll find a larger beta, and then sort of at the end of when we finally found the beta we want, we immediately shrink it down to exactly the size we need. And the final important property is that alpha doesn't falsify any axioms. So what Atserias and Dalmau proved and what we have argued in previous lectures, at least in one direction, I don't know if we did both directions. So assuming, just to get rid of pathological cases, if W is at least the width of the formula, then the width in resolution of refuting F is strictly larger than W if and only if there exists a memory W plus 1 defendant strategy. Okay. So if I have a defendant strategy in memory W plus 1, that gives me a W lower bound. The reason for this additive 1 is that basically when you do the proof to show that the prosecutor-defendant game is the same thing as resolution, this extra 1 is to deal with resolution steps and the extra variable that is resolvable. Now, and this, note that this was what immediately gave us the following theorem that says that the space, closed space in resolution of refuting F minus 3, which is the minimum closed space complexity of any refutation, is an upper bound on the width of refuting F minus the width K of refuting the formula. How did we, again, how did the proof for this go? Well, you just say that the one way of doing the proof is, suppose that we have a, or like a super quick proof sketch. Would be something like, well, suppose that the width of refuting F is S plus K minus 3. We want to show that the space of refuting F is at least S. So what do? We fix a resolution derivation pi with closed configurations C0, C1 up to C tau in space at most S minus 1. And then basically what we can argue is there exists a memory S plus K minus 3 defendant strategy. Okay, because if the width is this much, then the width is strictly larger than S plus K minus 4, which means that there is an S plus K minus 3 defendant strategy. So we just use this to find inductively for every configuration CT, we find an alpha sub T in the strategy such that alpha sub T satisfy this configuration, and then for bookkeeping purposes, we make sure that the domain size of alpha sub T is at most the space of C sub T. Okay, how do we do this? Well, basically the only interesting step is what happens as an axiom download. And what we will do at an axiom download, well, axioms have width at most K, and because of this slack, so axioms have width at most K, and we're also downloading, and the derivation has space at most S minus 1, and we're only downloading an axiom when we have room to download it plus do an inference step. Because otherwise we would just, if we're downloading an axiom and then immediately erasing something else, let's just swap these two steps and get a derivation in smaller space. So that means, in fact, that when we're downloading an axiom, we're only in space S minus 3. Okay? So therefore, assuming by the inductive hypothesis that we're good up to this point, I can afford to issue K queries as the prosecutor, okay, in order to create the lower bound, I act as the prosecutor. So I ask about all the variables in this downloaded axiom clause. And I can afford to do this, right? Because I can ask about K variables. I get an assignment to all of these K variables. At this point, we've fixed the value, the truth value of the axiom. Now, by property 4, this assignment must be satisfying, because otherwise it wouldn't be a strategy. Okay, but then I just pick the literal that is satisfied and throw away the rest. And now I can keep going. This is kind of the proof we did before also, but before I did it, before we used a space upper bound to somehow get a good prosecutor strategy, and now I'm kind of going in the other direction. I'm using the width lower bound and the prosecutor strategy to show how I can make sure that any derivation in too small space only derives satisfying things. Are we kind of happy with this? Okay. So, because it would be fantastic if we could kind of do the same to get total space lower bounds and also monomial space lower bounds. And we will use, in the same way, we now want to prove, so we're now going to prove total space lower bounds. So we're going to prove the following. Let me first state, actually, let me state this theorem over here to keep it on the board. So this is the theorem as done by Galesi, Kołodziejczyk, and Thapen. Suppose that F is a k-CNF formula. Suppose that R and S are, say, positive natural numbers. Let's say that R is at least k, so the axiom width. Suppose that we have a refutation pi such that each configuration contains less than S clauses less than or equal to at most S clauses of width strictly larger than R. Okay. Suppose there is a configuration style resolution refutation where I look at like how many clauses have width strictly larger than R, and I'll call them R wide or just wide. And let's say that I guarantee to you that in any configuration there are at most S such noticeably wide clauses. Then it holds that the width of refuting F is at most 2R plus S. This is our first technical main result. Is the statement clear? Okay, so now we claim that if we can get this, then we immediately get the total space lower bound of Ilario Bonacina, and in fact, I think they improve even the constants a little bit compared to what Ilario had. So this allows us to prove that if the width of refuting F is strictly larger than W, which is at most K, which is at least K, then the total space in resolution of refuting F is at least W over. So I'm writing it in this way with strict inequalities. We're not going to care too much about the additive slack here. There's like a plus minus ones or twos, but this statement is different. Okay, so maybe Let's see first that if we have this, then we're done. Okay. Well, so this is the proof of the corollary. Suppose we have a refutation of F such that the total space is at most W squared over 8. Now let me set R to be W over 4. Let me set S to be W over 2. And if we want to be careful, I think we actually let us round down so that we're sure to get integers. Well, I claim that clearly no configuration has more than S clauses of width strictly more than R. Because then we wouldn't be, I mean, if a configuration has more than S clauses of width more than R, then we're not staying within our total space upper bound. Okay, but now let's use the theorem. Hence, the width of refuting F is less than 2R plus S, which, as it happens, is W. So all of the heavy lifting is going to be here. R. Yeah. I mean, I certainly do need our. Is there some annoying? I mean, okay, let's maybe take that offline. It's sort of, I would say, we only care about this for large width. Sure. But you're right. I don't remember if we need some kind of special case for this, or if we just. I think the theorem is true as stated. I agree that if the width is like if the width is now my suspicion, but I admit to blanking, I think you could probably do some, just handle this special case somehow. We're interested in, I mean, the really interesting parameter here is when width is, like, K, you should think of it as constant. Width, you should think of it as polynomial, like, you know, square root n or something, or at least logarithmic, like. So you should think of, I think you should think of this as being, like, large enough. But yes, so just to point out that as stated, I am not making sure that I'm satisfying this condition. But I think this is, yeah, it's a very valid objection. I apologize, I missed this. So I'll leave it as homework for you guys. But is it clear that, I mean, we're really interested in when we have a good with lower bounds, at least a super constant lower bound. I mean, that's not an excuse for stating an invalid theorem, but the scenario of interest is then when W is non-constant and K is constant, or at least when W is asymptotically larger than K. Still, we need to fix the special case where W would be very, very small. I think you could probably do some special handling of this. Okay, so let's see. Let's see how the proof goes. So here is our proof pi. And let's just envision it as time is on the x-axis, and here is like how I envision the, maybe the configurations, if you wish. Slabs. So this is pi. It is a pi is actually, let me give some room. Pi C0, C1, C tau. Is a refutation as in the statement of the theorem. And now here comes the first, okay, so, sorry, let me continue a bit more to not get ahead of myself. So if we look at any configuration CT in pi, let's just use the notation that we have, and terminology, we have narrow clauses, and I'll call the narrow clauses C1 up to CQ. CQ could be very large, and I don't know how many these clauses are, except I know that their width is the most R. But from the point of view of this theorem, like all narrow clauses are free, we don't pay for them at all. Okay, and then we have some wide clauses. And for those, I know I have D1, D2, all the way up to ds prime, for s prime is at most s. And for those, the width of dj is strictly larger than r. Okay? And now, suppose that contrary to what the theorem says, that the refutation width is strictly larger than 2r plus s. And then fix a memory 2r plus s plus 1 dependent strategy. And note that here in this theorem statement, we want to make sure that our memory is at least larger than the width, but since R is larger than the width, we have quite a bit of slack here. Okay, so now let's start looking at the right-hand side of, so this is like time 0, time 1. Over here we have time tau. I'll start scanning from the end. Clearly we're deriving contradiction. So at some point, this dependent strategy A is starting to violate clauses. It violates contradiction, right? And at some point even it starts violating narrow clauses. So let R be the first time that happens. The minimum T such that there exists a narrow C in C sub T and some alpha such that alpha sets C to false. Okay? Let's suppose that this happens here. Here is this clause. Okay? So, C is not an axiom, right? C is a narrow clause, but it can't be an axiom because we're never violating axioms. So it's derived by resolution. Okay, so C is A or B for, say, A or X, B or not X, that are in C sub T minus 1. And now, without loss of generality, let me pick this alpha of size at most R. Because, well, it's a narrow clause, it has width at most R. Yes? So in particular, we can extend alpha to alpha prime, assigning X. Right? Because the strategy has size 2R plus S plus 1, so there's tons of slack. So alpha assigns X either true or false. We're clearly fully symmetric at this point. So, so firstly, alpha prime is now at most R plus 1 in size. And without loss of generality, alpha prime sets X to true. Sorry, let me decide that it sets X to true. But then alpha prime sets B or not X to false. Hence, what do we have now? Okay, so let me actually make some room here. Now I claim that we have alpha prime B or X, not X, is false, and this is a wide clause. Why is it a wide clause? Well, otherwise it is a narrow clause, and I could have picked R to be R minus 1. Right? R is the minimum. It's the first time I can find anything in the strategy that violates a narrow clause. So are we happy with this? Okay. Okay, fantastic. Now let's look at the other side. Start scanning from the left. Let L be the largest possible value T, such that T is strictly less than R, and there exists a beta that extends R a alpha prime. Beta is in the strategy. By the way, this is going to be a general feature today. Like any assignment, it's very important that we stay inside our defendant strategy. I'll try to remember to write it down. If I forget to write it down, it's still true. So like pretty much all the alphas and betas you see on the board, unless I tell you otherwise, are always inside the strategy. And note now again that there are definitely betas containing alpha prime that are in the strategy, because alpha prime, as assignments in the strategy go, is still fairly small. Okay. I'm interested in the maximum L, which the maximum T, the maximum L that I'm interested in maximizing T strictly less than R, so that I can find some assignment in the strategy such that beta actually satisfies all wide clauses in the configuration CP. Okay. Note that the assignments in this strategy could do three things. They can satisfy clauses, they can falsify clauses, and since these are partial assignments, they can also fail to have an opinion. Maybe they falsify a few literals but leave a few literals outside. Okay, but I'm looking at the first time I can find a configuration so that regardless of what super assignment of alpha prime you pick, you cannot fix all wide clauses in the configuration to true. Okay. So one thing that I did, so firstly here I should have argued that R is at most tau, but that we sort of said because we said over here we have contradiction, which is clearly a narrow clause that is violated. So that tells you that this is well defined. How do I know that L is well defined? Well, if you think of it, we start with the empty configuration. And the empty configuration doesn't contain any wide clauses. And then if you think about it, we actually start by downloading two axioms at least. And then maybe we make a resolution step. So at least L is something like at least 3 or something. Okay, is this making sense? Okay, so now fix. Now, given that I've chosen L, we fix such a beta, and we note that without loss of duality, let's see how large beta is. Well, beta is at most size of alpha prime plus S, because there are at most S wide clauses, and I need at most one literal each for them, right? Okay, so doing the math, this is then at most R plus S plus 1, which we note is still below the bound. So there's still some wiggle room. This is important for us. We can't keep extending beta. Okay. Note that alpha is contained in beta, and note that alpha sets the wide clause B or X to false, and therefore I know that L is in fact strictly less than R minus 1, right? Because over here, this is time step R minus 1, and alpha here, and therefore definitely alpha prime violates this wide clause. So L is somewhere over here. So by the maximality now of L, we have that C sub L plus 1 is C sub L plus some wide clause D. And D is not satisfied by any gamma that is, so note that at time L, we had a beta that was good. At time L plus 1, there is no gamma that is a superset of alpha prime minus 1 that satisfies everything. So definitely, it's not the case that gamma superset beta is satisfied by any gamma in the strategy. Am I making sense? So CL is the last time when I could have a beta that satisfies everything. So here beta satisfies all white clauses. Are you with me? And here we have a D that is not satisfied. I don't know what happens to it. Maybe it's false. More likely, somehow, any gamma containing beta just maybe fails to have an opinion. I don't know. Maybe this is a super white clause, right? It could be very white. You don't know. D is not an axiom clause. Why? Well, because the width of D is strictly larger than R, which is at least K. So this is where we need this condition. So you agree with me that this D is not an axiom clause? Okay, but then it was derived, right, by resolution. So what was the resolution? Well, then D is A prime or B prime, where for A prime or Y, B prime or not Y, which were in C sub L. So let's write this down carefully because we're getting close to the finish. D prime is A prime or B prime, or A prime or Y, B prime or not Y in C sub L. And now we still have room. Oh, by the way, this I. We still have room because R is positive. So let me ask about. Let me suppose that the defendant. So firstly, yeah. So suppose that the defendant is at this point in time playing beta. Let me ask about Y. So extend beta to beta prime. That also assigns Y. And again, we're fully symmetric at this point. So beta prime of Y is true, say. And of course, beta prime is living in the defendant strategy. So without loss of generality, beta sets Y, sorry, this is a Y, beta sets Y to true. And also without loss of generality, what's the size of beta? Well, the size of beta is size of beta prime is size of beta plus 1 at most, which is R plus S plus 2. Which is still small enough because R is positive. Now, I claim, or Galesi, Kołodziejczyk, and Thapen claim that at this point we can conclude okay, I didn't write this point right. I claim that there is a gamma in the strategy and gamma is a superset of beta prime, and gamma sets beta prime or not y to true. Okay. I claim that this cannot be. This will lead to contradiction. So let's maybe see how this gives us a contradiction, and then let's see why this should be true. Well, if gamma of beta prime of y is true, and gamma extends beta prime, that means that gamma of b prime is in fact true, because we know that it's setting y to false. Okay, so gamma sets the clause b prime to true, but b prime is contained in D, right? So then gamma, in fact, sets D to true. But we agreed by the maximality of L. I mean, this, now you realize that, well, if I would have picked that gamma, and I now would have picked L to be L plus 1. Right? So the fact that L was maximum meant that once we found L, and once we found the clause D that said why we cannot go further, then in particular we agreed that there cannot be any gamma that is a superset of B that satisfies D. But I'm claiming that what we've seen so far gave me such a gamma. That just cannot be. Okay? But of course I have not proven this. But this is not so hard. This is going to be a case analysis. So to conclude the proof, we have two cases. So case one is that B prime or not Y is a Y clause. Okay, but then we're done. Then definitely beta satisfies B prime or not Y. Because at this point, beta satisfies all Y clauses in this configuration. Are you with me? So clearly B prime or not Y cannot be a Y clause. Okay, so then it has to be narrow. And note that we also have already y in the domain of beta prime. Now we can ask for r minus 1 more variables. I.e. the variables in beta prime that are not already in the domain. Okay, do we have room for this? Hopefully we do. Beta prime has size r plus s plus 2. We have space r minus 1. Okay. So now this gives us a gamma in A. Gamma is a superassignment of beta prime. And as I said, we had space to do this. Gamma prime is at most beta prime plus r minus 1, which is at most 2r plus s plus 1. So we're hitting the budget limit right here. Okay. So since if we look at b prime or y, all of these variables are in the domain of gamma. Gamma, in fact, gives a value, a truth value, to this clause, b prime or not 1. By the minimality of R, note that this is a narrow clause, and gamma is in the strategy, and let's look at how we defined R. R was the first time when we found some narrow clause that was derived somewhere and some assignment in the strategy that violated this clause. This happened for the first time here, but now we're here. So by the minimality of R, gamma has no choice but to set this clause to true. And that again leads to converge. Done. Okay, so I think this is a good place to take a break. Let me just leave you with 2 questions. I'm erasing, by the way, these properties of dependent strategies. We're going to use them heavily for the rest of the lecture today, so I hope you burn the definitions into your brains. So question 1, can this proof be made, let me call it defendant oblivious, and let me explain what I mean by this. You know that there's a very, if you thought about how we did the proof for resolution and closed space being an upper bound on width, we basically just said, okay, now I have a small space refutation. And then I just said, basically, suppose there is a width lower bound. Suppose there is a dependent strategy. I don't care what it is. Let's just play it. And the fact that I could do this actually led to, like, if I turn this around, I could say, suppose there's a, I could use the the small space refutation to actually give a winning prosecutor strategy. And that actually gave me the possibility to turn a space-efficient proof into a narrow proof, which we did towards the very end of the lecture when we talked about this result. So it somehow was very explicit. I could actually syntactically, like, so one way of seeing it is, again, if I want to prove that clause space is a lower bound, is an upper bound of width, equivalently, if I want to prove that resolution width is a lower bound of resolution clause space, I just take a formula, I fix the dependent strategy, and then I just say throw any low space refutation at me and I'll just keep playing forever. Or flipping this around, given any small space refutation, I will transform it very concretely, syntactically, algorithmically into a low width refutation. Right? So sorry for beating around the bush, but note that this proof here is very, very different. I say first, suppose that there is a refutation where in every configuration, at most S clauses have large width, larger than R. And suppose at the same time that I have a width lower bound that I know to be false. Like this refutation and the dependent strategy, they do not both exist at the same time. And from the fact that they do not exist at the same time, I get a proof by contradiction. So I know that, and that kind of tells me, okay, it isn't possible at the same time that there is a refutation with few wide clauses in every configuration. That is not consistent with a strong width lower bound for the formula. But this doesn't tell me that, like, the theorem should tell me more than this. It should somehow say, well, suppose that I get a refutation like this. Let me turn it into a narrow refutation. And note that our proof very much does not do that. Are you with me? So it's kind of weird to have to argue, and what I mean by defendant oblivious in particular, you're saying, okay, suppose that I have a small space refutation, and I have a defendant strategy in large memory, which is not possible. And then I say, in this contradictory world, let me inspect the defendant strategy and define these left and right endpoints of the interval in my proof configuration and derive a contradiction from that. So it's very non-black box, like you actually have to give me the defendant strategy and I have to inspect it and define R and then define L and then force a contradiction. Which is somehow very, very non-constructive compared to how we did it before. I don't know if I'm making sense. So somehow one question is, can this proof be made more defendant oblivious and constructive? In the same way that there is a constructive version of Atserias and Dalmau, but this is very non-constructive. This is just a proof by contradiction, and when the dust settles, we're left by, we're left with nothing but some confusion, I think. I don't know about you. I still feel a bit confused about this proof. And the truth of the theorem it states. And then the Bonacina width squared lower bound, as we saw, was an easy corollary of this. Except for this fudge factor with what do we do if R is too small. Okay, so that's question one. Question two, that is even more interesting, is, well, can we get something like this for, could we get an analogous result for total space in polynomial calculus resolution? And here we have absolutely no guidance, because note that how heavily we used resolution. I mean, we're really using resolution width to get this defendant strategy, and this is what we're using throughout the proof. So this doesn't really tell us anything, okay, sorry. Actually, let me take that back. So we're using the width lower bound. Well, yes. Let me take back that I took this back. So we're using the combinatorial characterization of width. And we're using that. Somehow the reason that everything in the proof lines up is that we need to be in the same proof system, because then we know that we're deriving new contradiction exactly by the resolution rule, and then so we know kind of here that we only need to query one single variable because the resolution step only eliminates a single variable. This is somehow key here. So you could think of like, what would happen if you would try to do something like this for PCR? Well, then I guess one thing that could happen is that, well, it's not even clear if this would work. And in particular, when you go from one configuration to the next, maybe you're canceling not only variables, but some high degree terms or something. I don't know. So I think these are two good questions. But it's high time for a break. Any questions on this before we take a break? I want to stress again that I think this is a really interesting, the total space being width squared, to me this is a surprisingly strong result. And what is even more surprising is this very clean and simple proof. We just characterize resolution width, and then out of thin air we just pull this quadratic lower bound. And there's nothing advanced, nothing like how did this happen? I think this is an amazing result. Okay, let's take a break. So we are back after the break, and now we're going to talk about PCR space lower bounds, except we're going to do lower bounds in a fairly strong setting. I'm not going to emphasize this, except let me just tell you what the formal setting is, so that we have it in mind, and then we'll forget about it. But whenever I talk about PCR space lower bounds, this is actually what I'm going to mean. So I'll tell you this, and then we'll try to make sense of the lower bound we did before the break, and try to generalize it and see if we can prove PCR space lower bounds. We're actually a lower bound in this setting. This proof system has appeared in different settings going back all the way to Alekhnovich, Spencer-Somras, Boram, and Victorson. Slightly different flavors. This is my own take, but very much inspired by ABRW and by Galesi, Kołodziejczyk, Thapen. The point is basically you take the strongest proof system for which the space lower bound works. And that is the following. So a configuration is just a Boolean function. Okay? So any configuration is just a Boolean function. The space of the function is the arity. And now, where do monomials come into the picture? Well, the point is that with every Boolean function of arity S, you associate S monomials. And to evaluate whether the configuration is true or false under an assignment, you first apply the assignment to all the monomials, and you get 0 or 1. And then you plug that into the Boolean function and check whether that Boolean function is true or false. Okay, it's kind of clear that I can do this. Clearly, I can do this for clauses. Clearly, I can do this for polynomials. And in fact, it's not so much more general, because we know that, well, any Boolean function like this is in fact representable as a multilinear polynomial. Okay, so it's slightly more general, but it's not like it's out of this world more general. And now in function, let's refer to this as a functional monomial calculus, or FMC configuration. And now an FMC refutation would be the following. We start with the arity 0 function identity true. We end with the arity 0 function identity false. In particular, those have space 0. And then we say that you go from a configuration to the next in two ways. Either you can download an axiom, which, since we are interested in CNF formulas today, this is just adding a monomial and requiring that that monomial should value to 0, which is true, except I'm trying to avoid identifying 0 and 1 with true and false, just not to confuse ourselves. Or inference captures both erasure and inference, just saying that you can, if it's true that mt minus 1 implies mt, then you're good. Note that implicit in this notation is that mt plus 1 has its pick of monomials, MT has its pick of monomials which could be completely distinct, but this implication notation still makes perfect sense if it is true for any truth value assignment that this configuration implies this configuration, then it's a valid inference. Okay, in particular, and note that I'm only, regardless of how complicated this Boolean function is, I'm only charging you for the number of monomials you need to express this function. If it's a complicated polynomials where many of these monomials appear multiple times, you don't have to pay for them. So in particular, I claim that if you take any PCR refutation you can write in this formalism, and this space measure would just count the number of distinct monomials. But potentially this is more powerful. Is this definition making some sense? Okay. So what happened in the proof we just did for total space? Well, we fixed the defendant strategy. And then kind of what we look at some derived clause, C, and then we had two cases. We said that alpha satisfies C if, well, it sets some literal in this clause to true, which for now when we go in the monomial world, this will correspond to setting some literal in this monomial to 0. But then the other notion that we had, remember that then we started talking about wide clauses that were not satisfied. And in fact, what we did was we said that, okay, I don't know how much sense this makes, but what we kind of argued was that alpha kind of falsifies C if no beta containing alpha in the strategy satisfies C. And then you can extend, so now we can say that we're sort of saying that alpha satisfies a clause if it satisfies it, and we kind of say that it kind of falsifies it if it doesn't have an opinion and neither has any extension as long as we stay inside the strategy. And now once you have this notion for individual clauses, you can extend it to clause configurations. And then we basically showed, or we could kind of say that one way of viewing the proof is that it never happens that it can never happen that alpha satisfies CT and kind of falsifies within quotes as C sub T plus 1. And the reason this could never happen for us was that we argued that's when we needed to extend to some beta, and then we had this argument that actually beta was forced. We found a beta that was small enough but actually had an opinion. Okay, so this is one way of viewing how we looked at the proof, but then it is a fact that basically every alpha in the strategy actually satisfies C0 and kind of falsifies, or actually truly falsifies, C sub tau. Okay? And then we just use these two facts to somehow force a transition point. We found some point in time where we switched. At this point in time, under this notion of satisfiability, we had a transition, but that was impossible. this is kind of what happened. Maybe this is helpful. If so, great. If this is not so helpful, then ignore what I just said up to now. We are going to focus on this notion, because this is going to be useful for us. So again, we're fixing from now on, just to be clear, and we said this already before the break, but we have, from now on, we fix a k-CNF formula F. We fix a memory W dependent strategy, which will be curly A. And as I said, always, from now on, when you see alpha and beta, they will always live in curly A. And maybe I'll have the energy to write it out. If I don't have the energy to write it out, it's like crucial for all the argument that I would always stay inside A. Will that be possible? That depends on how large W is, right? So we want, ideally, we want as memory large strategies as possible, which we know corresponds to strong with lower bounds. One important thing also that I haven't stressed, but let me say it once. So when I talk about assignments, remember in the context of algebraic proof systems, on the one hand, I said that, oh, x and x bar are formally speaking distinct variables. This is not the case for alpha and beta. Alpha and beta are only aware of x and y and z. So like we don't think of, oh, alpha could set x and x bar to independently. Like all alphas and beta, they always respect the meaning of negations of literals. Okay. However, this kind of satisfies and kind of falsifies that will develop now. It's not so clear that this notion will respect this, but we'll get there. Okay. So now I want to define forcing. And this forcing is something that apparently is heavily used in logic, parts of logic. It's used in bounded arithmetic, which is the connection to proof complexity. And I freely admit that bounded arithmetic is one area that I think I would be helped if I knew more about. Some of the early breakthroughs, some of the strongest lower bounds we have come from bounded arithmetic, but have it's always been possible to rephrase them without using any trace of bounded arithmetic, pretty much. But it seems it can still be a helpful tool, but it's a bit of a steep learning curve. And we're not going to do, in particular, I don't know bounded arithmetic. We're not going to do any bounded arithmetic in this course. But what Galesi, Kołodziejczyk, and Thapen tell us is that forcing, as done in bounded arithmetic and model theory and logic, is what inspired their lower bounds. So let's look at their inspiration. So M is a monomial, always. M will always be, from now on, a monomial over the literals of F. But again, assignments are always to variables. Now, we say that alpha forces M equals 0 if alpha actually sets L to 0 for some literal L in the monomial. Okay? So alpha forces a monomial to 0 if it actually zeros the monomial. Maybe it doesn't set all literals, but you know, as soon as it sets one literal to 0, we kind of know what this monomial evaluates to, right? Alpha forces M to 1 if no beta that is a superset of alpha and lives inside the strategy sets M to 0. So maybe there is no alpha, maybe M is super high degree, maybe the defendant strategy has such a small W that we cannot even assign all literals in this high degree monomial. But I'm saying, well, for all practical purposes, if there is nothing, if there is no beta extension of alpha, that zeroes out the monomial, then for all practical purposes, the monomial will be 1. Okay? Why? Well, because this is a helpful definition for us. And we will write for this, we'll write that m is forced to the value b, b is 0. By the way, from now, for the rest of today's lecture, what we're going to do, in some sense, it's all going to be utter trivialities. We're just going to take this notion and then we're going to push it further and further and further until we suddenly have a monomial space lower bound that is square root of resolution width. Nothing difficult is going to happen, except that conceptually this is a bit of a weird measure, so you maybe have to help me a weird notion. So like whenever something doesn't make sense, you should ask, and then I'll remind you why what we're doing is in fact obvious. Because it somehow isn't obvious, except I'll explain it to you and hopefully we'll agree it's obvious. But it's a little bit, I don't know, I personally find it a bit weird. I should also say that in the original paper, Galesi, Kołodziejczyk, and Thapen, they say for forcing, and they say that m is forced if one of these two things happens, and if so, alpha fixes or decides m. Sorry, the other way around. They call this notion, like forcing to a value is forcing, but just the fact that it is forced to either true or false, they just use the word decide for this, or fixes. But we say that alpha decides m if one of these two things holds. So basically alpha decides m if alpha forces m to 0 or if alpha forces m to 1. I'm mentioning this just in case you want to look at the paper. I didn't quite understand why we need both forcing and decide, so I'll just use forcing all the way through consistently. It's possible that I'm doing some very weird thing now over in logic, where it's obvious to people why you should use different words, but it's not obvious to me, so I'll just use force for everything. Okay, the first thing that we want to say is that, well, the first observation now, and this is going to be observation 4 for us, and then I'm going to erase it, so we'll have to remember that this is observation 4. If alpha decides that m is b, then for all beta that are supersets of alpha and live inside the strategy, it also holds that beta forces m to the same value. And in particular, it can never be that any beta actually assigns m and assigns it to the opposite value. That can never happen. And this is obvious by definition. Well, firstly, because if alpha forces m to 0, then it's already setting a literal to false, and no beta can change that. And forcing to 1 is this condition by definition, that no larger beta has the opposite opinion. Okay? So this is one sense in which we're now forcing is this kind of satisfies, falsifies. So the interesting thing now that we will start working in is this will mean that relative to a defendant strategy, even a very small assignment will be able to sort of assign, quote unquote, very high degree monomials. In the sense that, well, if there is no expansion that makes the monomial 0, then we consider the monomial being assigned to 1. Okay, and now we just say the obvious thing that if P is a monomial, AI MI, and if alpha forces mi to some values bi such that C is equal to AI bi, then I will say that alpha forces P to C. So if there are truth values such that alpha forces all monomials in a polynomial to these truth values, and if these truth values multiplied by the coefficient sum up to C in the field, then I will say that alpha forces the polynomial to have value C. And we'll say that alpha forces P to true. Let's say that alpha forces P if alpha forces P to 0. And now obviously alpha forces M to true if for all polynomials in the memory configuration M, alpha forces P to true. Nothing strange here, like we're just extending this notion in the most natural way. And then I say that alpha forces P to false if alpha forces P to some value C that is non-zero. Alpha forces M to false if alpha forces all P in M and forces some P and for some P alpha forces P to false. Okay, we need the same notion for functional monomial calculus. There it's much easier. Basically, alpha forces monomial calculus configuration if it just forces the monomials to values, and then I just plug them in this Boolean function and see what I get. Is this making sense? Okay, so this is the notion that we're going to work with now. We're not going to look at assignments making configurations true or false. We're just going to look at configurations being forced to true or false. Okay? You have to be a little bit careful. Okay? Let's see why we need to be a little bit careful. Okay. Here's the first weird thing. Suppose that alpha is in the family, but alpha has maximal size, and suppose x is not in the domain of alpha. Then you realize just by staring at the definition that alpha forces x to 1, but alpha also forces x bar to 1. Which is kind of not nice for us because we would like to have these forced to different values, but we lost this. However, note that I'm crucially using that I'm at the boundary. Note that as soon as I have, if I would have a strict inequality here, if alpha is strictly less than b, then this is impossible. Why? And this could never ever happen. Well, simply because there is room to extend alpha to a beta that has an opinion about x, and then either this or this will be forced to 0. So as long as I'm below my budget, I'm respecting negation. But if I ever hit the boundary exactly, then all bets are off. Is this making sense? Okay. In particular, so here's another maybe helpful observation as we try to get a hold on this. So, and this we're going to use heavily. So suppose that alpha is in our strategy, and suppose that alpha is small enough. So we have a slack that is k, which is the width of the clauses in our CNF formula. So suppose this holds, and suppose that C is an axiom clause. Then obviously, as we've argued, there is a beta extending alpha, a beta inside the strategy, such that beta C is true. And hence, it can never be the case alpha does not force C to false. Okay, or equivalently, since we're moving into the monomial space, if we look at the monomial representing C, alpha does never force the monomial representing C to 1. Is this making sense? And now, here's another interesting scenario. I don't know if you remember this. Let's see. So remember that before we had this problem that suppose we have a formula that looks something like this. F is F prime, and then we have a bunch of axioms. I goes from 1 to n, xi negated. Okay. So in particular, this means that over in the these polynomials are 1 minus xi. And suppose that we had a polynomial configuration. Actually, let me write it m. And suppose we downloaded all of these 1 minus xi for I in n. And we wanted to have, okay, so we had m sub t here, and then what we did is we were trying to match this with an alpha in our strategy that would fix this configuration to true, right? And what we did was our alpha t just set all the xi's to 1. And that was fine because, okay, this assignment had size n, but we had 2 n monomials. But then the polynomial calculus derivation did some magic stuff, and we got to mt plus 1, where we had 1 minus product I goes from 1 to n xi. And now alpha sub t was no longer good, right? Or it was good, but it was way too large, because now we have 2 monomials and we can't afford to set n variables. But note that now I claim that if we have a family alpha, it must hold for all alpha in A, that in fact alpha forces this polynomial to true. Why? Well, because it's in the family, and because these are axioms, if I ask you about any individual xi, as long as you're inside as long as you're below w, you would never ever extend to make one of these 0, because that would violate one of the axioms, right? So in fact, in this setting, when we're using forcing, we suddenly see that actually an assignment of size 0 is forcing this highly problematic configuration to true. Am I making any sense? Like, do you remember that this is where we were worried before? So this sort of tells us that forcing is a way of somehow magically sometimes getting rid of high degree monomials without assigning them. And this is somehow what this whole thing is about. Okay. And what was this observation? The proof of this observation, well, we already did it, right? I mean, the point is that since alpha is this small, for the variables in C that are not in the domain, I'll just ask about them. Okay. And now I will extend alpha to a beta that has an opinion about all of the variables in C. And since beta is in the strategy, it has to satisfy C. And therefore, by this definition, you see there was an extension that zeroed out the monomial, that made the clause true. So therefore, it cannot be that alpha forces any axiom clause to false. Okay. We'll see how far we get today. We might not get all of the way, but we'll try to at least develop the machinery, and then okay. Worst case, I guess we'll have to continue with this tomorrow and adapt our planning a bit, but that wouldn't be the first time. Okay, here's a super important observation. Suppose alpha is in our family, and suppose M is any configuration. Now is the point where actually this is a functional monomial calculus configuration. I don't care, it's a Boolean. It's just a M from now on, fat style M is just a Boolean function evaluated on monomials. So it could be PCR, it could be functional monomial calculus, I don't care. Everything we do from now on will be valid for functional monomial calculus, therefore in particular for PCR. So I claim that it's never the case that alpha forces M to true and also forces M to false. That can never be the case. Like it could be that alpha doesn't have an opinion, but it can never force a configuration to both true and false. Okay, why? Well, by definition, it's never the case that alpha can force a monomial to both 0 and 1. Note that, so when I talked about forcing a polynomial, I just made an existential statement. I said that we force the polynomial p, do we still have it on the board? Yes. Alpha forces a polynomial p to C if there exists bi such that this is true. But the point is there can only, for any monomial and any fixed alpha, there can only exist a single bi. Maybe it doesn't exist, but if it exists, there's only one. Okay? So alpha can never force a monomial to both true and false. That means that for the same reason, it's never the case that alpha can force p to be true and p to be false. And hence, it can never force a configuration to be both true. So again, we can have the fact that truth value assignments don't force something, but they cannot force inconsistently. Okay? So next, suppose that alpha is an assignment in our strategy. Suppose that we have S monomials. Then, so clearly, like, what are we saying now that, okay, you can never force something to both true and false. And now the name of the game is we want to force things, because somehow we're going to try to do the kind of proofs we did before, but before we were actually honestly assigning configurations to true, and we had a configuration and we were assigning we had a refutation and we were assigning all the configurations in the refutations to true, and finally we had to reach the end, which is contradiction, and contradiction is not true, and therefore we got our lower bound. Okay, sort of our high-level idea now, our hope, this will crash a bit, but we'll deal with it when we get there. Our hope for now is we'll just do exactly the same thing, but with forcing. Okay, that's our idea. We'll note that this didn't quite pan out already for our total space lower bound. It was slightly different because we didn't start at one end and move inductively. We sort of scanned from both ends and met in the middle. But that's fine, right? I mean, if that's what's needed, you can agree that we can do that, right? I mean, as long as we get the lower bound. So our idea is somehow, some kind of maybe meet in the middle, but basically from one side, we're going to force configurations to false. From the other side, we're going to force configurations to true. Somewhere we're hit in the middle, and then we say, well, you can't force things to both true and false. So this is will be an important observation that will help us clinch the contradiction. But now, clearly, for this to work, we need to force things. Yes? Okay, so this is what the next lemma says, that suppose that we have some alphas, suppose that we have some monomials that unfortunately maybe are not forced, right? That would be very sad. What can we do? Well, then we say that there is a beta containing alpha that is in the strategy such that beta forces all mi, and the size of beta is at most the size of alpha plus s. Note that I'm not saying what beta forces mi to. Maybe it sets, maybe some of the monomials vanish. Maybe some of the monomials are in fact high degree monomials set to 1. But beta does the forcing and it's not too large. Okay, what's the proof? Well, we can do this by induction. And in fact, it's sufficient to just consider M1. It's kind of clear that if I can do this for a single monomial, then I'll just repeat this. Yes, are you happy with this? But now, just by definition, so we have two cases. Like case 1, if there exists a beta larger than alpha, such that beta, sorry, let me stay consistent with my notes. Suppose that there exists a gamma in alpha. Gamma lives in the strategy, as always. And gamma sets L to false for some literal in M1. Then we set beta to be alpha union L is set to false, and this is a subset of beta. Beta is in the strategy, and since sorry, this should be gamma, right? Gamma is in the strategy by assumption. Beta is a subset, so it's also in the strategy, and it's definitely forcing forcing M1 to 0. And now case 2 is otherwise we in fact have by definition that alpha already forces M1 to 1. Right? So we're good. Okay. Okay. The next interesting assignment is, the next interesting lemma says basically that forcing is always possible to realize. Like, there's always a truth value assignment that is consistent with the forcing. Let me write this down. Suppose that alpha, and this is we're taking care of, we're saying that example 5 is a pathological example that cannot really happen for us. So suppose alpha is in the strategy, alpha is not of maximal size. And suppose alpha forces mi to di for S monomials m1 up to ms. Then the claim is that alpha can be extended to a truth value assignment alpha prime such that, and note that now I'm talking about actual truth value assignments, that mi by alpha star, mi is assigned to bi. Okay, so if we have a forcing relation, there is some truth value assignment that is consistent with this forcing. Maybe this alpha star will be super large, but at least it exists. And this will be very useful for us, but we should prove this. And the proof is very short. We do the obvious thing. We set alpha star, first we let so we start with letting alpha star be alpha, and then we extend alpha star with L equals 1 for all L in M such that alpha forces M to 1. And that's my alpha star. Okay. Now let's for a second move out into the dual space where we have x and x bar. It's clear that in this space, just by definition, alpha star is assigning all monomials in the right way, right? So the only thing we need to worry about is, so alpha star is a truth value assignment. Unless there exists M prime, M double prime, such that X is in M prime, X bar is in M double prime, and alpha forces M prime to 1, and alpha also forces M double prime to 1. Do you agree with me that this is the only thing that could go wrong? Okay, but this is impossible because alpha is small enough that we can actually extend to a beta that assigns a value to x. And that beta will zero out either M prime or M double prime. It's conceivable that there could be, there could be betas that actually, there could be beta prime that sets x to 0. There could be beta double prime that sets x bar to 0. That could be the case. But what it definitely cannot be the case, I mean, at least one beta will have an opinion of x and will set x to either 0 or 1. So this is impossible. Okay, so now I think we're getting to a point where I want to prove one more lemma, probably. Let's see how we're doing on that. Yeah, I want to prove one more lemma, and then we'll take stock of where we are, and then we'll have to call it a day. And then tomorrow we'll have two more technical lemmas, and then we'll put all the pieces together. But basically, we're already in a very good place. We can namely now prove the following interesting. Remember that one part of what I want to do, one part of what we had in our previous inductive argument, we said that, well, for every memory configuration at time t, we find an alpha t that satisfies it. And then by induction at time t plus 1, we find an alpha t plus 1. Okay? We're now at a point where we can kind of do that step. Okay? So namely, so since this is an important lemma, let us write down what we have. So alpha curly A is a memory W dependent strategy. F is a k-CNF formula, and now W and K are both positive numbers. In fact, I want K to be at least 2, which is kind of not a big restriction. In fact, later anything we prove will only be interesting for K greater or equal to 3, because it's an exercise that 2 CNF formulas, in fact, have constant space complexity when it comes to flow space. So they're not so fun. Okay, so this is the setting. Curly A is a memory W dependent strategy. F is a k-CNF formula, non-trivial in the sense that K is at least 2. And we also suppose that alpha in curly A has size at most W minus K. And we kind of already know what that means. That means that we can throw any axiom clause at alpha and we'll be able to extend. So alpha could not possibly force an axiom to false. That's kind of the idea, right? Let M and M prime be successive configurations in either in functional monomial calculus or in polynomial calculus in a derivation from M. Then I claim that it cannot be that alpha forces M to true, and then the next configuration M prime is, alpha forces M prime to false. Okay, again, it can be that alpha doesn't have an opinion, but if we can make it have an opinion, it will have the same opinion for both. Right, so now you already see the game plan now that everything forces the initial configuration to true. So as long as we can do the forcing relation, by induction we're going to force things to false, to true, but clearly no alpha can force contradiction to true. Are you with me? Okay, I mean, we're going to run into problems, but kind of, at least for now, things are looking moderately good. Okay, so let's maybe prove this lemma and then think about wrapping up. And then we didn't do quite what we wanted to do today, but maybe that was because our plans were unrealistic all along. Okay, so what does a functional monomial calculus do? Well, either it holds that M either it honestly holds that M implies M prime, or M prime is in fact M union some axiom C in F. Right? In both cases, I claim that if I can prove this lemma for the following statement, that there is a C in F such that M union C implies M prime. If I can prove the lemma under this assumptions, then you should be happy. This is sort of, just for simplicity, takes care of two cases. I'm just saying, suppose that there exists a C such that M union C within curly brackets implies M prime, then it cannot be that an alpha decides M to true and not M prime to false. That's what I'm going to prove, and this clearly takes care of both of these cases. Yes? Okay. So let's argue by contradiction. So suppose, in fact, alpha does force M to true, and alpha forces M prime to false. Now, since alpha is less equal W minus K, we extend to a beta such that all variables of C are in the domain of beta. Yes? Okay, then we know, since beta is since beta is also in the strategy, clearly beta says C to true. Now, without loss of generality, we can pick beta to be of size alpha plus 1, right? I just pick the large beta and then I shrink it to the literal that satisfies C. And note that this is less equal W minus K plus 1, strictly less than W. Here I'm using that K is at least 2. Okay, so now let's just look at all the monomials appearing anywhere. Let them be M1, M2, all the way up to MS. Alpha decides both M and M prime. So for every Mi, there is a Bi such that alpha sets M, forces Mi to Bi. Right? Otherwise, this would not hold. Okay. But then beta also forces all Mi's to Bi's, right? By definition, like the things that are forced to 0, they're actually assigned to 0 by alpha. And if you're forcing to 1, then by the definition of forcing, it means that there is no larger beta that would zero out the monomial. Remember, we had this very early observation 4. I warned you I would erase it. Observation 4 said that if alpha forces something, then all supersets beta inside the strategy force to the same value. Okay? We're still in agreement about this? Okay, good. This is by the observation 4 that we erased. Okay, but that means in fact that beta forces M union C, right? Because beta forces M, and actually beta honestly, here I'm overloading notation. This actually means that beta zeroes out the monomial that represents C. Okay? And beta actually honestly sets the monomial representing C to 0, and beta forces M by what we just said. And beta also forces not M. Okay, now we're ready to use lemma 10 to get a beta star, so that actually beta star honestly sets M union C to true, and beta star honestly sets M prime, sorry, I forgot the prime there, to false. Because what does it mean that beta forces not M prime? It means that beta forces all monomials in M, and it forces it for polynomial calculus resolution, it forces it so that some polynomial values to non-zero, that is violated. And for the functional monomial calculus, okay, this I should have written down, they're forcing not M just means that if you force the monomials to their values and then evaluate, then actually M prime evaluates to false, which means that the Boolean function not M prime evaluates to true. And note that again, the important thing is that forcing is always in the context of forcing monomials to values, and lemma 10 just said that if I force a bunch of monomials to values, then there is a truth value assignment that does this. So if beta is a truth value assignment that forces all monomials in a functional monomial calculus configuration, then I just take beta star to actually assign these values, and when I honestly evaluate the Boolean function on this beta star, it will then evaluate M prime. Okay, but now we're done, right? Because this contradicts that M union C semantically implies M star. And that's where we start. Okay, so we have time to do one desperate proof attempt, and it will crash, and then we'll get very depressed and we'll call it a day. So here's the idea. Proof idea 1. We have given pi, which is M0, M1, all the way up to M tau. Alpha 0 equal the empty assignment is such that alpha 0 forces M0 to true, right? Now, given alpha t minus 1, that forces m t minus 1, then basically what we want to do is we use lemma 9 to find that alpha t that in fact is a superset of alpha t minus 1. So alpha t clearly still forces mt minus 1 because it's a superset of alpha t, and also alpha t forces all monomials in m sub t. Okay. Now, by the lemma we just proved, we get that alpha t actually forces mt to true. Right? Because it cannot be for successive configuration that an alpha forces one of them to false and the other one to true. Okay? So we just keep going until we hit m tau, which contain contradictions, and then we're done. Does this make sense? Okay, what's the problem? Why aren't we done now? Why will we need one more lecture? Alpha grows. Alpha grows. By how much? Alpha t, so potentially alpha t might be alpha t minus 1 plus s, right? We only have the guarantee of an increase s. Okay, and a priori we don't know how long this derivation is. So we will need the w that we're shooting for will be the space bound times the length of the derivation. And derivation we could expect to be, like at least linear probably. So in order for this to work, we would like a width lower bound that is maybe quadratic in the number of variables or something, which might be a tough ask. What are we missing? Like, why didn't we run into this problem before when we did the PCR space lower bounds? Because we had a locality lemma, right? Remember that we were sweating a lot whenever we had an erasure step. That's where we crashed before. But note that we had an erasure step to deal with these problematic, dangerous configurations that you could derive. But note that, we didn't have that problem, right? We looked at that configuration that caused us a problem before, and we were somehow able to deal with that problem by actually an empty assignment. But in general, we don't know how to deal with, you have a derivation and space ebbs and flows, and you do it over different monomials. So we're missing a locality lemma. Okay. Can we get a locality lemma? So what would a locality lemma say? A locality lemma would say something like, suppose alpha forces m to true, suppose the space of m is not too large, then there is a very small alpha that also forces the configuration. But now the property of forcing comes to bite us. Maybe we were forcing m to true because alpha was somewhat large, so that all betas extending alpha had no opinions about something. But now suddenly when we need to shrink alpha to alpha prime, then maybe there are smaller beta primes that force, that assign variables in high degree monomials in both ways, and we lost the forcing. So it's not even clear if we can have a locality lemma. And in fact, that's a great question. Like, can we combine this with some kind of locality lemma? Okay. So what we're going to do instead is, we'll have to do it tomorrow. We'll have to scan the proof from both ends. So basically we're gonna, here is the proof, and we're gonna have alpha 0 that forces this guy and this guy, and then we grow this to some alpha 1 which forces maybe this configuration and this configuration. And then we're gonna have alpha 1 is going to be contained in alpha 2 that maybe forces this configuration and this configuration. So we're going to get smaller and smaller intervals. So we're going to apply the forcing construction S times, roughly. Okay, and we know that in every time we grow by S. Okay, so hence this will work if the width lower bound W is something like S squared. Okay, this is exactly where we lose the square root. And we have, what we've done today, like we have everything in place now to do this, except that it's, you know, getting uncomfortably close to 4 p.m. and we probably have 1 more hour to go. So, so I think we're calling it today. But this, again, this is our plan. We're going to find assignments inside the family that force configurations. By growing these assignment sizes very, very carefully, we'll force things that at the beginning we know that we're forcing the first configuration to true, the last configuration to false. By growing our assignments very, very carefully, we will narrow this interval until we have an interval that is so small that we can afford to force everything inside this interval. And then we'll actually do this. You know, once we have a small interval where we can actually force everything, then we'll just go by induction inside that interval, and getting a little bit ahead of ourselves. In fact, we'll need S squared plus K, because once we're forcing close enough, then we're going to go step by actually asking like about the axioms one by one. Okay, and again, like all of the technical details we are on the board, and we need 3 more technical lemmas, and we'll do them tomorrow, and maybe we'll also revisit some of this stuff to make sure that we have it in cache. And then we'll have to think about how to do about the size degree trade-offs. We'll still try to do maybe some size degree trade-offs, but not everything that we plan for. Questions at this point about any total space lower bound, or about forcing, what we did so far? Again, we talked about, just to say, I don't know if we said this on the recording, regarding the total space being width squared lower bound. I think we agreed that it should hold if the width lower bound for the CNF formula is at least 4 times the initial width, and this might be a condition that you need to add. But morally, the proof we did, you know, modulo this problem at the low end of the interval, the proof that we did should be fine. Okay, then let's call it a day.